this session. So now actually we will be hearing the contributed talks. So the first talk will be on defining reachability tree under adiabatic and reflexive boundary condition. The authors are Nazma, Naskar and BK Sivaraj. They are from KIIT deemed to be University Bhubaneswar, India. And the talk will be delivered by Nazma Naskar. So what to you, Nazma?
Thank you, Shukarna. Is my screen visible?
Yes, visible.
Very good morning to all of you.
Oh, you are muted. We cannot hear you.
Oh, she's audible. Oh, she's audible. Najma, continue.
Okay, sir. So very good morning, all of you. Myself, Nazma Naskar, and today I am going to present that defining reachability tree under adiabatic and reflexive boundary condition. And in this paper, my co-author is BK Sivaraj. And in this regards, we're going to discuss about in the next few minutes that what motivates us to take this topic as our research topic. And to understand this, we need to understand some basic terminologies of cellular automata. After that, we'll go into our contributory sections. That is the definition of reachability tree under adiabatic boundary condition and the reflexive boundary conditions. So first of all, that from the day when the concept of cellular automata is conceptualized by the J. von Neumann, it was assumed that the size of the lattice is infinite. And with these days, the CA is going to apply it for the different field of science and also this technology. Implement the infinite lattice size in the technical applications. So additional interesting feature is added, the boundary condition. And in this regard, in the boundary conditions, we have the different type of boundary conditions such as null boundary condition, periodic boundary condition, adiabatic boundary condition, reflexive boundary condition, and intermediate boundary condition. However, in the most of the work still that is considered as first two boundary condition, that is null boundary condition and periodic boundary condition. And one of the efficient characterization tool of both of this boundary condition is reachability tree, via which we can identify the reachable state, whether the CA is cyclic or acyclic, reversible or irreversible, counting the number of cycles. All these things can be done efficiently characterized by this reachability tree. So this makes us to think that whether this tool we can apply to the other boundary condition or not. And here we are only going to discuss about the adiabatic boundary condition and this reflexive boundary condition. So that first we'll go back to some few terminologies of cellular automata. That first we'll need to know that what is cellular automata. That it is actually the arrangement of the set of cells forming a lattice, and each lattice has a discrete set of integers, and this is called the state. And the cell variables are changed simultaneously at the discrete time and space. And also the local interactions of the cell can simulate this complex behavior. These are some basic features of the cellular automata. Keep this basic feature as constant. There is lots of variation is found, and among them, the simplest one is the elementary cellular automata, which takes one dimension, two state, and three neighborhood. That any state can change to its next state depending on the self, left state, and this right state. And the collection of the state at any time t is called the configuration. Now, if we so till now we get to know that any state that we have the two states and the number of and the dependency is based on the three state, that is self, left, and right. Hence, at the present state can be the 2 to the power 3 number of combinations. And if I convert these numbers, binary numbers, into the decimal number, then we'll get the rule mean term or the RMTs. And these RMTs are ith RMT is dependent on the I plus 1, that is the next RMT. So this right RMT is dependent on this present state, and this dependency is depicted in this table. And in this now we have this 8 RMTs, and 8 RMT can be filled with the value either 0 or 1. So the number of combination we will get 2 to the power 8, and this called us as a rule. And using all this rule, we will get the elementary CA or the elementary CA. Now come to this, the finite, as we told earlier, as I told earlier, that whenever we have the concept of the finite CA, then the boundary condition is introduced. And the first we'll discuss about this periodic boundary condition, and any n cell CA will denote that the leftmost cell will be cell 0 and the rightmost cell will be cell n-1. If I have the n number of cells are there. So in case of the periodic boundary condition, the left of cell 0 is assumed to be equal to the value of cell n-1. And the right of the cell n-1 is assumed to be equal to the cell 0. And in this, if I arrange our cell in this way, then we will have this periodic boundary condition. And next, if I assume the left of cell 0 and the right of cell 0 is filled with the logic 0, then we will get the null boundary condition. Next, and after that, how we'll calculate this RMT? We'll assume that there is a 3-cell window which will slide among the left of the cell 0 to the right of the cell n-1. So in our first case, in this diagram, so at the first window is loaded with a value 0, 1, 1, which gives the RMT 3. Next, I will slide this window to the one cell right. That will be, then the window will be loaded with the value 1, 1, 1, which gives us this RMT 7. And in this way, we can calculate the RMTs of any configurations, and this sequence of RMT will be called as the RMT sequence. And this is in this way we can calculate the RMT sequence for the any given configurations for the any boundary conditions. So now come back. So these are the two well-known boundary conditions in the world of cellular automata. Here we are going to discuss about this adiabatic boundary condition. The left of cell 0 is equal to the value of cell 0 in case of adiabatic boundary condition, and the right of the cell n-1 equal to the value of cell n-1. This is the condition of adiabatic. And in case of the reflexive boundary condition, the left of cell 0 will be filled up with the cell equal to the value of cell 1, and the right of cell n- will be equal to the value of cell n-2. So these are the architectures, or these are the cell arrangement we can assume in the adiabatic boundary condition and the reflexive boundary condition. Now come back to this. What is the reachability tree? As I told, I told earlier that reachability tree is a characterization tool. Now, what is it? It is basically a binary tree, and moreover, we can say that it is a rooted edge level binary tree. The left edge of this reachability tree is represent 0 and the right edge of this tree is represent 1. For n cell CA, we'll have n plus 1 number of labels, and the characterizations know that this tree is characterized by the 3 component, that is node, edge, and label. Label and edge are the subset of the 8 RMTs, and edge is the connection between the previous node, previous level node, and the present level node. Whenever any level is empty set, then the corresponding edge will be called as non-reachable edge. So in case of constructing this reachability tree, so we'll start with the cell 0 and I will traverse up to the cell n-1. Now for the cell 0, with the number of RMT all RMTs, all 8 RMT will be not valid, or we need not consider all 8 RMTs. Now why we so what are the valid RMTs there? As I know that the left of cell 0 is denoted by the -1. Now this state of this 2 cell, the state of cell 0 and -1 always same. That we can say that present state and for the first window, at this first window, the present state and the previous state will be same. That if the present state is 0, then our previous state is also 0. If the present state is 1, then the previous state is also 1. And the next stage will be appear exhaustively. So we have our RMT windows will be filled up with or loaded with the restricted value, that is all 0, 0, 0, 1, 1, 1, 0, and all 1. So in this root level, only I will get this 4 valid RMT, that is 0, 1, 6, and 7. Now similarly, for the right boundary, the cell n-1 and cell n, which is the left or which is the right of cell n-1, will be equal. That means here the present state and the next state will be same, and the previous state will appear exhaustively. Hence, for this one, I will we have the configurations will be 0. Present state is 0. Then the next state will be 0. Next, we can have the 1 in the previous state. Present state, if the present state is 0, then the next state is 0. In this way, we'll have this valid RMT at 0, 4, 3, and 7. So with this valid RMTs, we can define our reachability in this way, that any intermediate level node and the levels will be the subset of the 8 RMTs. And for the root level, only the valid RMTs are 0, 1, 6, 7, which is denoted by X, X, Y. And the nodes of the n-1 level will be loaded with the valid RMT will be 0, 3, 4, and 7. So first we'll consider this. So we'll consider this rule vector under adiabatic condition, that say that our root node is loaded with 0, 1, 6, 7. So for constructing these edges, I will refer the first rule or the 0th rule, that is 162. 0 has value 0, so it will be appear into the left edge. 6 has value 0, so it will also appear into the left edge. The RMT 1 and 7 has the value 1, so it will be appear into the right edge. Now from 0 and 6, we'll derive the next valid RMTs using the table or relation table of ith and the I plus 1th relation, that is 0, 1, 4, 5. And next, for the construction of the next level, we'll refer the first rule, rule 1, that is 136, and so on and so forth. We will construct this tree at the nth level, some RMT we will ignore, and so we'll just keep the only this valid RMT which I will calculate it in the previous slide, that is 0437. So this is the adiabatic boundary condition. Now for the verification that whether it is correctly represent the state transition or diagram or not, here we can see that the 0 is a reachable state. In our, according to the reachability, 0 is a reachable state, and here also in the state transition diagram we can see, yes, all 0 is a reachable state, and it is come from the state all 0 0 0, and also that is come from the state 6 6 4 0 0. So here it is this, so we can see that this all in this state transition diagram, the same state there is 0 0 is reachable from the same state also. In now next we can see that 0 0 1 0, that this gray state, the gray node is non-reachable node, that is 0 0 1 0. So here we can see that 0 0 1 0 is also a non-reachable state in the state transition diagram. Now in case of the reflexive boundary condition, similarly that some of the RMTs of the root level are valid and some of the invalid, and at the last level or the n-1th level some RMTs are valid, and not all RMTs are valid at the last level. So how we'll calculate? So this derivation can be take that cell 1, that is the previous state, and the next state, the value of previous state and the next state is always same, and the present state will be exhaustively appeared. So whenever our previous state, next state is 0, so our previous state will be 0. Whenever our next state is 1, our previous state also take 1. So in this way, we'll get the 4 combination, that is 0 0 0, 0 1 0, 1 0 1, and all 1. That is, if I'll take the decimal value, it will take 0257. At the right boundary also we'll get the same same RMTs, as we know that same RMTs appear. Here is also the present state and the previous state will be same, only the present state will appear exhaustively. Hence the same set of RMT will be valid at the root level and the n-1 level. For the same rule, here I'll depict the reachability tree on the reflexive boundary condition, that here according to this rule, so first RMT at the root level we have 0257 will be valid, and the last level also the same set of RMT will be valid, and the intermediate levels are created using the rule 162, 136, 130, and 202. So for this verification, here we can see that all 0 state is reachable state, and the gray node which represent the state 0010 is non-reachable. So you can see here, yes, this 0010 is 0011 is the non-reachable state. So we can say that reachability trees correctly represent the reflexive boundary condition CA also. So in this paper we'll discuss about, or we'll explore the reachability tree under adiabatic boundary condition and reflexive boundary condition, and it is almost same as the null boundary condition, that only the values of the root level and the n-1th level RMT will be changed. So the all properties of the null boundary null tree, reachability tree under null boundary condition can be applicable into the reflexive boundary condition and the adiabatic boundary condition. So to do this, we'll identify the valid RMTs of the 0th cell and n-1th cell. The computational complexity is linear to identify the reachable state and the non-reachable state. Moreover, this is we can serve or we can consider this paper as the base paper, and we can apply all the properties of null boundary reachability tree to the adiabatic and the reflexive boundary condition. This is the future scope and as well as the motivations of our work, that actually our previous work, I'll see that I'll consider the null boundary condition and periodic boundary condition, and this CAs are applied to the pattern classification, and some of the data set produce the better result in null boundary condition, and some data sets are produced better result in the from here, it is interesting to see that if I will consider the other boundary condition as the pattern classification, what will be the effect and how much changes are there? How much changes are there? And same type of observation we can also do for the generation of pseudo number generation and in the field of the cryptography. So that would be the interesting to take what is the effect of the other applications of general technology, where we applied the null boundary and the periodic boundary, and using this concept, the concept of all this logic and theory can map to the adiabatic boundary condition and reflexive boundary condition. We can map it is very easily. So this is our future scope and also our motivation, as I told earlier. And here are some set of references which I refer for this paper. And thank you everyone for your time and attention. So if you have any questions.
Thank you, Nazma. So now the audiences are requested to ask the question if you have any question.
I am. Hello. Hello. I'm audible.
You're audible, but your voice is breaking.
Now it's okay.
Yes.
Is it okay now?
Yeah, yes.
Okay. First of all, thank you for. Okay. First of all, thank you for this good presentation, because you can find and construct the reachability other side from null and periodic boundary condition, just like adiabatic and reflexive boundary condition. So my first question is, like adiabatic boundary condition looks like null boundary condition. So what is the main difference between null and adiabatic boundary condition? That's not only for the n-1th level. There is another difference.
No, there is no, just the boundary condition in the null boundary condition in the both left and rightmost, I will consider the logic 0. And in case of the adiabatic boundary condition, whatever the value of cell 0, it may be 0 or 1. In the left, it will be, so we are not restrict our leftmost and rightmost cell to the logic 0. It can take the logic 0 and 1 also. So the structure will be more or less same. We can say that the structure of the reachability tree or the construction principle of the reachability tree, we can say that 90% are same, but due to the small difference, there is a huge impact on the state transition diagram. Just for this one, in this slide, we can see that the same rule, the same CAIL considered into the adiabatic boundary condition and the reflexive boundary condition, and this
no. And then another question for like complexity, like worst case complexity for reachability in null and periodic boundary condition is always exponential. So for that, boundary condition is also exponential.
It is for the dependent
No,
on the problem.
worst case will be exponential, but for average case it's maybe less.
The worst case is exponential for the based on the problem nature. If I wanted to counting the cycles, so then it will be taking the exponential. Then definitely the reachability tree under adiabatic and reflexive boundary condition also takes the exponential.
Okay. Last question is, can I get maximal length cycle using this adiabatic boundary condition?
As I said, from my assumption is that definitely we can get, but it need to means explore. I'll not explore here, but from the intuition, definitely we can get.
Okay.
Thank you, Shumit.
Thank you. Thank you.
Okay, any more question?
Nazma,
Yes,
okay. So you have said about reversibility under this adiabatic boundary condition and reflexive boundary condition. Have you started thinking on it?
Yes, I started working on it, and basically right now we have that scheme to synthesize. I'm working on the synthesize scheme, which can be applied irrespective of the boundary condition. That using reachability tree, there's much similarities we have. So irrespective of the boundary condition, any scheme which can synthesize any CA under any bound applicable to any boundary condition.
Have you noticed any difference between this null boundary condition and this adiabatic boundary condition? Any difference you have noticed? Have you noticed?
Right now, sir, this is under means consideration. Till now, not that much time. Till now, will not get that much result. But definitely, with the time, I will take on the consideration of this problem. That what is actually this is our problem. That what is the difference I am getting for. So right now, there is no some remarkable difference I will get, but definitely I will get with this.
Thank you. Thank you. Thank you.
Okay, any more question?
I have a question. For this, actually, for this for one particular problem, this boundary condition is arrived, or as generalized this boundary condition is arrived.
Your voice is again breaking.
Internet connection is not good. Now I am audible.
Yeah, now it is clear.
Is it okay?
It is fine.
Okay, okay. Like for some particular problem, this boundary condition is arrived, or as generalized, this boundary condition is arrived.
That this is our future scope that we wanted to generalize the boundary, all of the scheme we wanted to generalize. That's maybe the finding of reversibility or synthesize some reversible. These are the problem right now. I'll consider for the future. And these are the future scope of this paper.
Actually, my question is why this boundary condition is developed. That means for one particular problem or for generalized version.
So for the generalized version.
Okay. 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 Thank you.
Okay. Any more question? Okay, Nazma, I have just one question. You have used already the periodic boundary and null boundary for pattern classification. So what's your intention to use these two boundary conditions? Do you want to see an improvement on the data sets or something else?
See that is there is an improvement or not. And along with that, I wanted to also create some relations between the data set and the boundary of condition of. I wanted to find, is there any relation between the data set or the boundary condition? If some data set is producing the good result into the null boundary condition, but not in the periodic boundary condition or the other boundary condition, what is the reason behind this? What is the nature of this data set that for which this higher accuracy or the better performance we are getting. And the same for the other boundary condition. I wanted to explore this thing.
Thank you so much, Nazma, for your nice presentation. So